Let us look at kernel of group homomorphism. Let G be a group under an operation star and G prime be another group under a operation star prime. Now, let's say E is in G, the identity, and E prime is the identity of G prime. Then the homomorphism F maps G to G prime. What the kernel of a group homomorphism means is that it is the set of elements of G that maps to the identity of the group G prime. And this is how it is written, that definition. Kernel of F is equal to K, which is equal to the set of elements in G which maps to the identity of the second group. So K is called the kernel of F, and K is a normal subgroup of G. If F of A is an element of G. So if F of A is equal to E prime, implies that A is in the kernel of F. If X and Y both are in the kernel of F, then F of X times Y inverse is equal to F of X times. This is the operation of the second group. F of Y inverse, and F of X, because it is in kernel, is equal to E prime, and F of Y inverse is also in the kernel of F. How? Because Y is in the kernel, that means its inverse is also in the kernel. E prime times E prime is equal to E prime, which implies that X times Y inverse is in the kernel of F. So kernel of F is a subgroup of G. Remember, this is a one-line proof for or proving that a set of elements is a subgroup. Now, for any K in K and G in G, F of the conjugation of K with the elements of G is equal to F of G times F of K times F of G inverse. Now here the operations are all from the second group. Now F of G remains as it is because it may or may not be in the kernel. But we know F of K is equal to E prime. Why? Because K is in the kernel. And F of G inverse is equal to F of G inverse. Again, G may or may not be in the kernel. So which is equal to F of G times F of G inverse. And here each is the inverse of the other. So when we multiply them, we get E prime. So that implies kernel of F is a normal subgroup of G. So here we just put it as a statement, and we have proved that kernel of F is a normal subgroup of G. If G maps the group G to the group G prime, then kernel of G is equal to K prime, which is equal to the set of elements in G such that G of X is equal to E prime. So basically now we have two kernels of homomorphism, K and K prime. These two will not be equal to each other since F and G are different. Of course, if they are the same, then they will be equal. Cosets Ka will be in the kernel if F of X equal to F of A. Let's see how we can make this statement. Let X be in G and kernel of F equal to K. Let X and A in G map to the same element in G prime. Their quotient X times A inverse must lie in the kernel of F. How? f of x times A inverse is equal to f of x times f of A inverse, which is equal to f of A. Why? Because f of x is equal to f of A. So we substitute f of A times f of A inverse. And the product of these will be E prime. So that means since f of x times A inverse is mapping to E prime, that means x times A inverse lies in the kernel of f. That implies that x belongs to the coset k times A or ka. Now let's prove this very quickly. F of x equal to f of A, because x and A maps to the same element in G prime. We have already shown that f of x times A inverse is equal to E prime, which implies x times A inverse is in K, which implies x is in Ka. But if we multiply on both sides by A inverse times A will become E, and here you will end up with Ka. So x is in the coset Ka. Now these cosets of the kernel are called the fibers. Basically, what does this mean? If H is a normal subgroup of G, then G by H forms cosets. So those cosets will map from G, or in other words, is a homomorphic image from the group G. This is written like this because this is a standard result. This homomorphism is given a special identifier, that is pi. So pi maps G to G by H, where pi of G is equal to G times the subgroup H. Let's look at some examples to understand this much better. Let G be a group of integers under addition, and G prime be a group of integers under addition modulo 3. And let the homomorphism F map from G to G prime, where f of n is equal to n mod 3. So the kernel of f is a set of all integers that maps to 0. So remember, here we have all the integers in this group. So all those integers which maps to the identity of G prime. And what is the identity? It is 0. So those set of elements of integers, group of integers under addition which maps to 0 is called the kernel of F. So kernel of F is equal to the set of elements in G where n mod 3 is equal to 0, which is 3z. All multiples of 3 will leave a remainder 0. And we can write it in the set form like this. So kernel of F is a normal subgroup of G. So that means 3z is a normal subgroup of Z. If A is equal to 1, then we say the fiber over 1 is a set of all integers that map to 1. And which are those elements? Those are the element 3z plus 1. So fiber over 0 is 3z plus 0. Fiber over 1 is 3z plus 1. Fiber over 2 is 3z plus 2. Now these three cosets or fibers partition G. Okay. So now let's look at another example. Given a group Q8, every subgroup of Q8 is normal. We know that. So the possible kernels of homomorphisms from Q8 are its subgroups. Now, 1 is the kernel. That is, a kernel contains only one element, 1. When F maps Q8 to Q8, where f of x equal to x. So here, every element of Q8 gets mapped to itself. by the homomorphism F. So that means which element maps to the identity? The identity itself. That is 1. So since 1 maps to 1 and no other elements maps to 1, we say kernel is the set containing 1. Let's take the center of the group Q8, which is 1 comma minus 1, written as Z of Q8. Now we have a homomorphism from Q8 to the quotient group Q8 by Z of Q8. The map F sends each element to its coset modulo Z of Q8. That is 1 comma minus 1, I comma minus I, J comma minus J, K comma minus K. Now, very quickly, you can make sure that you are, on the right track by observing that Q8 has 8 elements. Z of Q8 has 2 elements. That means 8 by 2, 4. There has to be 4 cosets. Now, the only elements of the quotient group Q8 by Z of Q8 that maps to identity is itself. Here the identity is 1 comma minus 1. So here 1 comma minus 1 is kernel under this homomorphism. Now let's look at the subgroup generated by I, which is 1 comma minus 1, I comma minus I. And you have a homomorphism F from Q8 to the quotient group Q8 by the subgroup generated by I. Now Q8 has 8 elements. The subgroup generated by I contains 4 elements. That means there will be 2 cosets. The map sends each element to its coset modulo R, and the only element of Q8 by the subgroup generated by I that maps to identity is itself. That is the subgroup generated by I itself. Subgroup generated by J is 1 comma minus 1 comma J comma minus J. And the homomorphism F maps Q8 to the quotient group Q8 by the subgroup generated by J. So the map sends each element to its coset modulo J. So the only element of Q8 by J that maps to identity is itself. Same logic here also. Subgroup generated by K is equal to 1 comma minus 1 K minus K. And the homomorphism F maps Q8 to the quotient group Q8 by K. And the map sends each element to its coset modulo K. And the only element of Q8 by the subgroup generated by K that maps to identity is itself. Finally, remember the group itself is a subgroup. So if we take that Q8 and you have a mapping F which takes Q8 to Q8, where f of x equal to 1. Now here every element maps to 1. So the kernel is Q8.